On Friday, we talked about confidence intervals for population proportions. Well, today we're going to look at confidence intervals for population means. And also how to find sample sizes and all that good stuff. So, like I said, we looked at on Friday at proportions. Now let's look at the mean of a population. Now, with the mean, there's going to be two different options. I say options. They're not options. It's based on what's given. One of them will be, they'll give us the population standard deviation. They'll give us sigma. That's one method. The other method is when sigma is unknown. So dual credit, if you'll notice, I actually split the homeworks, and the reason you have two homeworks is one homework deals with sigma being known. The other homework deals with sigma being unknown. So that's that. I will say a little bit of good news is I saw several of y'all struggled on the homework that was due last night, or Friday night, really. I gave y'all until last night. I looked at the test AC sent me. That topic's not on the test. Their period said the same thing. Hallelujah. Binomials won't be on the test. The 5.1 through 5.4, 6.1 to 6.3, homework-wise, are on the test. And just like the last test, this test comes almost directly from the homeworks. So study those. 5.4, and then 6.1 to 6.3. And these are the homework numbers. These aren't like the notes packet numbers.
5.1 through 5.4, 6.1 through 6.3.
Notes-wise, it would be chapter or section 7.6, and then chapters 8 and 9. Okay. So first one we're going to look at is confidence intervals when sigma is known. So if you're one, you like to color code your notes. Maybe you want to highlight or underline or something. Sigma is known, because this is the first method. So confidence intervals when sigma is known. Okay. So the general formula for a confidence interval for a population mean when the following three conditions have to be met. X bar has to be the sample mean from a random sample. The sample size n must be large. And the population standard deviation sigma must be known. If those three conditions are met, we can use the following formula to get our confidence interval. So X bar plus or minus the Z critical value times sigma divided by the square root of n. So when we work these problems, we're going to have to either A, write it down, or B, talk through it to make sure our conditions are met. You'll credit, you'll actually have a question that says, why can't you use this method? And you'll have to give me two reasons. AP That's just part of y'all's worked out solution when you do the problems. Okay, I want you to say sample's random, sample size is large, standard deviation's known, we meet all the requirements. That's just part of the solution. Think of it like a checklist. You're going through it. Okay, check, check, check. Got it. I can go. Okay. So you'll also notice that these are the same properties for the sampling distribution of X bar. Remember back to chapter 8. They have very similar properties. And this interval is appropriate even when it's small, so long as it's reasonable to think the population is normal. So I'm kind of walking you through. X bar is our point estimate. Sigma over the square root of n is the standard deviation of the statistic. The bound on our error is that whole right side after the plus or minus. I'm going to ask us this, when we're doing an experiment or a study, do we typically know the population standard deviation? No. If we did, we wouldn't really have much of a study to conduct. Because we know it. So typically that's not known. But in some cases it will be. The confidence interval is appropriate even when n is small, as long as we can assume it's normally distributed. So that's actually a blank. The population distribution is normal in shape. Here, let's look at an example. Cosmic radiation levels rise with increasing altitude, promoting researchers to consider how pilots and flight crews might be affected by increased exposure to cosmic radiation. A study reported a mean cosmic radiation dose of 219 millirems for a sample of flight personnel from Xinjiang Airlines. Suppose this mean is based on a random sample of 100 flight crew members, and let sigma, your notes has a typo in it. It says S. That should say let sigma equal 35 millirems.
That's what it should say.
That's what they should say. That's a sample. We don't want the sample standard deviation. We want population. So
instead of S, it's sigma, so sigma equals 35.
yes. Calculate and interpret a 95% confidence interval for the actual mean annual cosmic radiation exposure for the Xinjiang flight crew members.
So if the X on the left equals 35, typo or is it that circle thing? That's the typo.
So on your notes, this is what it should be. It shouldn't be S equals. It should be sigma equals. The notes themselves have the typo. Because the whole deal on this one is that sigma is known. Okay, so before we even can begin, we have to verify that our conditions are met. So I'm going to do this one with y'all here. So we need to calculate and interpret the confidence interval once conditions are met. Don't just jump into the calculation. The first thing we have to see, is it from a random sample? Let's see. Yep, they say based on a random sample right here. So, yes.
If one of the conditions isn't met, you just say no. Like, is that the problem? You just say no and the hard conditions are met.
You could, yeah. So, like, if it's not a random sample, we couldn't really calculate much. So, let's see. So, data is from a random sample. Let's go and say of flight crew members. Let's be specific here because they could be a random sample, but if they're testing the gate attendance, is that really doing much good? Okay, sample size, is our sample size large? Is it greater than 30? Yes. It says we have 100. N equals 100. So sample size is large. And I'm going to put in parentheses 100 is greater than or equal to 30. At least I hope it is. And then last condition that we have to have is sigma. We know sigma. Like I said, this is a typo. Yes, sigma is known. So we've met all the conditions. We can now proceed with our calculations. Let's make note of the information given down here. And then we can go from there. So let's see, what's X bar? What's our sample mean? What do they tell us our mean is? 219, that's right. Okay, do we know N? N's 100. What about sigma? $35 is what they tell us. And then we want to be 95% confident. So what would our Z critical value be? 1.96. So we have all our information we can compute. Now, I'm going to write the formula. That way we see where to plug everything in.
Use a Z crit on here, on the probability, right?
So, Z critical actually is down there in that little small table in the bottom.
Oh, okay.
We're 95% confident, so I think on y'all's it says C is 0.95. And then that goes with the value 1.96. Does that make sense?
Yes, sir.
T19 plus or minus 1.96 times 35 over the square root of 100. Remember, we want to calculate the error first. Don't just try to put the whole thing in your calculator. Like the 219 plus or minus. Get the error first, and then go from there. What do we get for our error? Our bound on the error, I should say. 6.86. Bless you. Which means our interval is what? Yep. 212.14 to 225.86. Okay, now our instructions here tell us to calculate, which we did, and interpret, which we have not done yet. So how can I put this into words? What can I say? We are 95% confident that the actual mean annual cosmic radiation exposure for the flight crew members is between, and now we use our range here. So 212.14 millirems and I'm out of room, 25.86. And I don't know how you actually say those units. I'm guessing the M is milli. I don't know what the REMS is. That's why I say millirems. Okay, questions on this one? No good. Okay. Next one, we have a ketchup bottling example. A certain filling machine has a true population standard deviation. That should be sigma again, not S. It's population, so that S should be a sigma. True population standard deviation sigma equals 0.228 ounces when used to fill ketchup bottles. A random sample of 36, supposedly 6-ounce bottles of ketchup was selected from the output from this machine, and the sample mean was 6.018 ounces. Find a 90% confidence interval to estimate the true mean fills from the machine. So here they just ask us to find the interval. We don't have to interpret it, we just have to find it. But before we find it, we have to go through and make sure. We don't have to write this down, unless you want to for completeness. But we have to go through and make sure. First, is it random? Do they tell us it's a random sample? Yes. So that marks off that random sample. Good. Now, sample size. Is it large? How do we know it's large? Greater than 30. 36 is our sample size. Do we know sigma? Yes. Sigma is 0.228. So do we meet all the requirements? Yes. Okay, we can proceed. So let's see, we know that sigma is 0.228. What about x bar? 6.018. N. And then our critical value. If we want a 90% confidence, 1.645, that's right. Okay, so let's set up our formula and solve it. X bar plus or minus the critical times sigma over the square root of n. Okay, plug everything in. 0.018 plus or minus 0.645. 8, 36. When you do your error bound, you type that in the calculator, what do you get to 3 decimal places? Just the bound. 0.063. Yeah. You're right, teammate. Just doing 3. Since our mean has 3 decimal places, We're doing 3 on the error. Okay, now for our actual interval itself. What would the lower bound be? .955.
That's 6.018 minus 0.063.
I'm sorry. And when I do 6.018 plus 0.063, what would I get? 6.081. Good. Now they don't ask us to interpret, they just say find it. Boom, we found it. Questions on this one? Okay, so now let me go back to my PowerPoint. Make sure I didn't miss anything. Okay, what would happen to the width of, let's go back to our Xinjiang airplane example. What would happen to the width of the interval if we instead said 90% instead of 95% confidence? The width would shrink. That's right. As we go down in confidence, the width shrinks. As we increase in confidence, the width increases. Okay. Make sure we did all that. Yep, we did. Okay, so that's when sigma is known. So pretty straightforward calculation. Now let's look at what happens when sigma is unknown. So when sigma is unknown, which is more typical, we use the sample standard deviation S to estimate sigma. In place of z-scores, we must use what are called t-statistics. We've got z-scores, now we have t-statistics. Any others?
T, an excellent line over it. Don't keep looking at him, my S in there in my hand. That's one quick.
So T is our x bar minus mu divided by our standard deviation. That's divided by the square root of n. Now, right now, we're not going to worry about calculating a t-statistic. When we get to hypothesis testing, we will. But notice, so it's not anything terribly new. It looks similar to our z-score, doesn't it? It looks similar, so nothing terribly new. To use the value of S, or the use, I should say, of the value of S, introduces extra variability. Therefore, our distribution of t values has more variability than the standard normal curve. We tend to say that T has fat tails. Let's look at some properties. T distributions are described by their degrees of freedom. And we'll talk about how to calculate degrees of freedom here in a second. But we describe them by their degrees of freedom. So the T distribution corresponding to any particular degree of freedom is bell-shaped and centered at 0. Sounds like another distribution we know of. Bell-shaped and centered at 0. Standard normal. That's right. However, this is different in that it's more spread out than the standard normal. So if we look at the picture on the screen, we have our z-curve, but then the t distribution with 2 degrees of freedom. Notice the peak doesn't go as high because the tails are thicker. We have to absorb that area somewhere. So we absorb it in the tails. Well, I kind of just answered that question. Why is the z-curve taller than the t-curve? Because the t-curve has thicker tails, so it's got to be shorter. The third property. As the number of degrees of freedom increases, the spread of the corresponding t distribution decreases. Right now, these facts kind of seem boring. Once we talk about the fourth fact, I'm going to tell y'all one that kind of makes me scratch my head. Really? Did that really happen? If we have our t-curve with 2 degrees of freedom, if I increase that to 8 degrees of freedom, watch what happens to the curve. It's taller. I've got more degrees of freedom, so I can be closer to the normal distribution. Which leads into property 4. As the number of degrees of freedom increases, the corresponding sequence of t distributions approaches the standard normal. And just a little fun fact for y'all. Actually, this fun fact is on dual credits test. So the guy that developed the T distribution worked for a beer company. He worked for Guinness Brewing Company and developed it. Okay. I don't know what he was drinking, but hey, it must have worked. Yep. The guy that developed this worked for Guinness Brewing Company. Okay. So for what degree of freedom would the t-distribution be approximately the same as the standard normal? And if you notice, 2 are kind of flat and low. Then we increase it to 5 and we get closer to the z-curve, which is the top one. How many degrees of freedom do you think we would have to get to until we're approximately normal? 7? And I heard 30. So even at 30, we wouldn't be exactly normal. We would, a t-distribution, you would pretty much have to go to infinity to get it to be standard normal. So as you can imagine, for the t-distribution, each degree of freedom requires its own table. But if you notice in your formula charts, I only have one t-table. I don't have an infinite number of tables. That's because for the t-distribution, usually all we're interested in is critical values. As far as this class is concerned, that's all we'll be interested in, is critical values. So your t-table, your t-distribution table, is just a table of critical values. And the way you would read it is you would look for the degrees of freedom on the side here. And then, depending on whether you're in AP or dual credit, either look along the top of the table or the bottom of the table for your confidence level. Dual credit, if you look at the top row of your table, it says confidence level. We all look at the top. AP, you actually have to look at the bottom of the second page of the table. And then remember, if it's on the first page, remember what column it's in and go find that same column on the first page. So it's a little bit more tricky, but it's there. So if we wanted 3 degrees of freedom with 95% confidence, then I would find 3 degrees of freedom, go over to 95% confidence, and that would be my critical value. Okay, so let's get back to our confidence intervals when sigma is unknown. So the general formula for a confidence interval for a population mean based on a sample of size n, when x bar is the sample mean from a random sample, we've got to have that still. The population distribution has to be normal, or the sample size n must be large. And the population standard deviation is unknown. So these are our 3 conditions we must meet here. These 3. If we meet those, then we can find the confidence interval. So x bar plus or minus t critical value times s, our sample standard deviation, divided by the square root of n. So to get the degrees of freedom for your T critical value, so to abbreviate degrees of freedom, we just say DF. DF equals N, your sample size, minus 1. The degrees of freedom is N minus 1. And this confidence interval is appropriate for small n only if they tell the population distribution is at least approximately normal. So if we have a small n, then we have to be told, or we have to figure out that we can say it's approximately normal. On the two examples we're going to work in class, we're going to have to quote unquote figure it out. Really, we're going to read a graph to get that data, but still, we have to look at it and figure it out. So let's look at our next example. The article, Chimps Aren't Charitable, summarized the results of a research study published in the journal Nature. I'll let y'all read the rest of that if you're interested on your own. I think it's kind of interesting about the study, but just to save time, I'll leave that to y'all. So they say the data represents the number of times out of 36 trials that each of the 7 chimps chose the option that provides food to both chimps. So they have another chimp in a separate cage. And essentially, if they pull one rope, he just gets food. If they pull another rope, both chimps get food. Okay. Compute a 99% confidence interval for the mean number of charitable responses. So let's put these values into L1 in our calculator and get the mean and sample standard deviation. So there's 7 values. Let's put them into L1 and get the one variable. And when you get the mean, if you don't mind letting us know to the 2 decimal places, which you get. Only 1.29, good. And then what about these sample standard deviation? 2 decimal places. Is that the sample? Is that S or is that sigma? 1.80. Good. Okay. Now, we did those calculations. Really, we were kind of putting the cart before the horse. We first need to verify that the conditions for a T confidence interval are met. So first, does it come from a random sample? doesn't really say, but for the sake of this example, we're going to suppose it. I mean, it's the first example in the notes. It'd be kind of a bummer to be like, oh, it doesn't work. Okay, throw it out. Let's go. So we're going to suppose it does. So, suppose it's reasonable to assume a random sample. Second thing, is our sample size large? This? How many chimps do we have? We only have 7 chimps. They do this experiment, they do 36 trials, but chimp-wise, we only have 7 chimps. So n is equal to 7, which is small. But we can't just stop and say, oh, nope, doesn't work. Because if we look at our properties, it says it has to be large or we have to figure out that it's normal. So I'm going to put a note here that says see chart on next page. And we'll get to that chart here in a second. And then the third one, do we know sigma? No. Okay, so let's look at the chart on the next page. What kind of plot is this? Anyone want to take a guess? We talked about them. What's that? It is? Yeah, it's a type of scatter plot. We talked about it at the end of chapter 7. It's a normal probability plot. And what do we look for on a normal probability plot? A linear pattern. Do we have a linear pattern here? Yes.
It's gotta be like resemble a straight line.
Gotta resemble a straight line, that's right. Now, I will say dual credit, don't freak out too bad about this. I won't have y'all checking normal probability plots and all that stuff on the test. So the plot is reasonably straight. So let's make a note of that up here. The plot is reasonably straight. So it's safe to assume normality. Okay, so we meet all 3 of our conditions, which means we can proceed with our calculations. What did we find our mean to be, x bar? 21.29. And then what about S? $1.80. Okay, we need to get degrees of freedom. How do I get that?
It's sample, right? This is sample.
S is the sample standard deviation. That's right. Degrees of freedom is n minus 1. What's our n? N is 7. So 7 minus 1 is 6. So for our t critical value, we need to look for 6 degrees of freedom. And how confident do we want to be? 99%. So 6 degrees of freedom with 99% confidence. So you'll look in your T table for 6 degrees of freedom, and then, like I said, 99% confidence. What do you get for your value? What? 3.707. Good. What's that? Next to T right here. So this is 6 degrees of freedom. That is our confidence level. This is when you write T, typically, and this is the way I'll write it, you do degrees of freedom, comma, your confidence level. Or, as we'll learn in the next unit, also something called the alpha level. Okay, so we have everything now to do our interval. So x bar plus or minus our t critical value times s divided by the square root of n. So that's going to be 21.29 plus or minus 3.707 times. Let's see, that says 1.80 over root of 7. To 3 decimal places, what do you get for your error bound? $2.522. Okay. Now, notice they give me the mean to 2 decimal places, x bar. Let's do our interval to 2 decimal places. So, what would my lower bound be to 2 decimal places? 18.77. And what would my upper value be? 23.81. Now ask me to interpret. Come on. So we're done with that one. Okay, now here's what I want y'all to do. I want y'all to try the television watching example. Work it the same exact way that we just did it and see what you get. Yes. Oh, y'all do that? I'm gonna step out and use the restroom right quick. Then I'll come back and we'll talk about it.
All right.
So try to see if you can get through this television watching example. Please. Yeah. Okay, anyone brave that want to share what they got?
I would be brave, but I ain't got it. So,
Okay, well, let's go through. Let's see, so let's make sure first we meet our requirements before we do anything. So, is the sample random? Yes. I say randomly selected. Is the sample large? No. How many do we have? What's our n? N equals 10. So what we need to do, look down here on our chart. So what do we notice about our chart here? Is it approximately linear? What can we assume? Yep. So normal plot, normal probability plot is approximately linear. Yes.
On the test, are you going to write out the conditions?
If it asks you to like explain, I would like y'all to.
But if it just says like, find it,
It just says find it. Now, on this one, the reason we had two with a chart here is, for one, I want to mention this output down here. So if you look at the bottom of the chart, you'll see something called the Anderson-Darling normality test. Typically, if this p-value, the p-value is that bottom number down here. Typically, if the p-value is greater than 0.05, then it's safe to assume normality. What's our p-value in this one? What's that? 0.7. Is that bigger than 0.05? Yeah. So we can assume normality. Okay. Now that we know it's normal, I guess our third condition, do we know sigma for this one? No. So we meet the requirements for a confidence interval using the t-distribution. Okay, let's do our calculation now. So what did y'all get when you put these into one variable stats for x bar?
86 and 11.4.
86, and then S is 11.84. Okay. Now, what's our n? What did we say it was? N equals 10. So degrees of freedom would be what? 9. Which means our T critical value means we need 9 degrees of freedom. And how confident do we want to be? 90%. If we look for that T critical value, what would that be? 0.833? Okay, now let's set up our interval. X bar plus or minus the T critical times S over the square root of N. 86 plus or minus 1.833 times S 7.84 divided by the square root of 10. What did you get for your error bound? 86 plus or minus what? 6.863, okay. Okay, and then for your lower bound, what'd you get? That's your low bound? 14. Okay. And for the upper bound? So what you got?
I do know.
Don't figure out where we messed up if you didn't get it. Okay, questions on calculating confidence intervals. Okay. Let me make sure I didn't skip anything. Okay, so for this one, I'm going to go back to the notes because this gives it to a specific, which you can write this down. So for choosing a sample size, the bound on error of estimation associated with a 95% confidence interval is 1.96 times sigma over the square root of n. If we solve this for n, we get n equals, and then 1.96 sigma divided by b, all squared. Now, this is for one specific case. 95% confidence interval. How could I make this to be generic? Where should the z crit go? That's right. That's right. So let's make sure we add that to the notes. I'm going to write both formulas, so if you didn't get them down, that's okay. So for the 95%, we said it was 1.9. the bound was 1.96 sigma over the square root of n. But in general, it is z crit times sigma over the square root of n. Again, if we solve each of these for n, we get 1.96 sigma over b all squared. Or if you want to generalize it, z critical times sigma over b all squared. So these two are generalized. This one is specific to the 95%. I'm going to underline that and put an arrow down there. Now, when sigma is unknown, a preliminary study can be performed to estimate sigma. Okay? Or, as we talked about last time, sometimes on these sample sizes, it's not reasonable to try to do a preliminary study. So we have to make an educated guess. This educated guess is down here. If the distribution is not too skewed, we can take the range and divide it by 4. So let's look at this last example. The Financial Aid Office wishes to estimate the mean cost of textbooks per quarter for students at a particular university. The estimate to be useful, it should be within $20 of the true value. What does $20 represent? B. How large a sample should be used with 95% confidence to achieve this level of accuracy? So if we're 95% confident, what's our z critical value? 1.96.
What is B again?
That's our bound on the error. So our error, we do not want it to be bigger than 20. Now, what's the one thing they did not give us in the problem? Sigma. So, note here that sigma is unknown. We must estimate. So sigma is approximately the range divided by 4. And they give us this range right here. They say the bookstore estimates that it goes, the price varies from $150 to $550. So $550 minus $150 divided by 4. What does that get you? 100. So sigma is approximately 100. Now we know enough to do our formula. N equals z crit times sigma.
What's Z critical?
That's our critical value for z.
Like, where do you find it?
It's on the bottom of your z table.
Oh, I see. I got you now.
And then divide it by our pound. We said the critical, oh, let me square it. The critical value is 1.96 times 100 divided by the bound of 20, all squared. What do you get for n? 96.04. we have to round up, and it equals 97.
Round up like regardless.
Regardless, that's right. Unless you get a whole number, then you can stop. If you get any kind of decimal, let's go up. Questions on 9.3? Okay, that is it for chapter 9 and the next test.
Better.